children, so here I am with the second video of the video series on squares and square roots class 8 maths, and in this video our agenda is to look at some interesting patterns of perfect squares, and we will also learn how do we find squares without actual multiples. Yes, now these are some of the basics which should be very strong for each one of you, and we will make it super duper interesting for you. So are you all ready to learn with me? Let's get started. Let us look at a very interesting pattern with square numbers. So the first few square numbers which we have discussed so far are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. So these are the squares of 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So let us look at the interesting pattern that I am talking about. So if you look at 1 is just 1. Okay, let's move on to 4. So 4 can be written as 1 plus 3. Yes, it can be written like that. 9 can be written as 1 plus 3 plus 5. Yes, we can write it this way. How about 16? It can be written as 1 plus 3 plus 5 plus 7. 25 can be written as 1 plus 3 plus 5 plus 7 plus 9. Now, do you notice any pattern by now? Well, what we see is every time as the number increases, as the value of the perfect square is increasing, we see that it is sum of odd numbers. Like 1 is the kind of smallest odd number. After that you have 3, then you have 5, then 7, then 9. So can you guess what would be, how can you express 36? So 36 can be written as 1 plus 3 plus 5 plus 7 plus 9 plus 11. 49 can be written as 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. So in this fashion, we see that this is true for all the perfect squares. Now, it is not possible for us to write all the perfect squares in like this, but we have just written the first 10 perfect squares like this. So, from this, we can make a generalized statement that if you are given any number and if you are asked if that number will be a perfect square or not, because when we deal with small numbers it is pretty easy to tell, but when you deal with larger numbers, like let's say if I give you 3,36,402, will this be a perfect square or not? So all these tricks would help you for dealing with larger numbers. So from this, the generalized expression, the generalized conclusion is that if a number is a perfect square, it has to be the sum of successive odd numbers starting from 1. So now the bigger the number is, the bigger the sum would be. Like if the number is in thousands, so it would be sum of some first n odd numbers. Now you might ask that, okay, but how do we find out the sum of first n odd numbers? Because what is n? N is the number of odd numbers. So as the perfect square value increases, the value of n also increases, right? That's what we see in this list. So when you look at this list, very clearly you can see that as n increases, n means how many odd numbers are there. So the value of n in this case is 1. The value of n in this case is 2 because there are 2 odd numbers. What is the value of n here? Here n is equal to 3. Here n is equal to 4. N is equal to 5 and so on. So we see that as the value of the perfect square increases, the value of n also increases. Okay. Now if I give you any number randomly, now it is very difficult for you to tell that how many odd numbers sum is that particular perfect square. So that's going to be really difficult. So what will you do? So in that for that purpose, what we do is we see that whenever you are given some odd numbers, so the sum of those first n odd numbers will always be n square, will always be given by n square. And what is this n square? This n square is nothing but a perfect square. Now let's say that if we talk about this sum. So here how many odd numbers are there? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 odd numbers. So n is equal to 8 in this case. Therefore, what would be the value of this sum? So the sum of first 8 odd numbers will be given by n square, that is 8 square. And 8 square is what? It is 64. So we can see 64 is equal to sum of these many odd numbers. So if we know the value of n, that is if we know how many odd numbers are present, in that case we can actually tell that the sum of those many odd numbers will be equal to which perfect square. Okay, so let us take this example. Let's see that using the concept of this interesting pattern, if we can determine whether a given number is a perfect square or not. So we take the example of 156 here. So how can we write 156? Now 156 is not a very small number. So let's start from the beginning. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. So till 19 when you reach, you know that you have reached 100. So now till here it is 100, then you add 21, so it becomes 121, then you add 23, then it becomes 144, then you add 25, so it becomes 169, but we need 156. So if we do the sum up to here, then it is 144. If we do the sum up to here, then it is 169, but we want 156. So 156 will lie somewhere between 144 and 169. Right, so that what does this mean? This means that 156 is not a perfect square, because had 156 been a perfect square, we would have got exact sum as 156, right? But in this case, we are not able to write 156 as the sum of first n odd numbers, because if we take, let's count the number of odd numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we take 12 odd numbers, then the sum of 12 odd numbers is 144. If we take 13 odd numbers, then the sum of 13 odd numbers is 169. But we want 156. This means that 156 cannot be expressed as the sum of first n odd numbers. Therefore, 156 is not a perfect square. So the conclusion here is, if a natural number cannot be expressed as a sum of successive odd natural numbers starting with 1, then it is not a perfect square. So let's take one more example. So here we have 169. So how can you write 169 in the similar fashion? 1 plus 3 plus 5 plus 7 plus 9, 11, 13, 15, 17, 19, 21, 23 and 25. So till 25, if you add this, you get the sum exactly as 169. So how do you sum this? You really do not need to add. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you have a total of, so the value of n here is 13. Therefore, the sum of first 13 odd numbers, sum of first 13 odd numbers will be given by n square, which is 13 square. 13 square is 169. So this shows that 169 can be expressed as the sum of successive odd natural numbers. Therefore, 169 is a perfect square. So now let's look at the next interesting pattern. In fact, with square numbers, you have a lot of interesting patterns. So this is just the second one. So this pattern says that a square of odd number is a sum of consecutive natural numbers. Okay, can you give some examples of square of odd number? So is 4 a square of odd number? No, because 4 is 2 square. So 2 is an even number. So 4 is not a square of odd number. Is 9 a square of odd number? Odd numbers, 9 is 3 square. So 3 is an odd number. So 9 is a square of odd number. So some examples of square of odd numbers would be 9, 25, 121, So 9 is 3 square. So it is square of odd number 3. 25 is 5 square. So square of odd number 5. 121 is 11 square. So this is also square of the odd number 11. So these are all examples of square of odd number. So this pattern says that the square of odd numbers can be written as sum of consecutive natural numbers. For example, here 9 can be written as 4 plus 5. So 4 and 5 are consecutive natural numbers. Similarly, 25 can be written as 12 plus 13. So 12 and 13 are also consecutive natural numbers. 121 can be written as 60 plus 61. So again, 60 and 61, they are also consecutive natural numbers. So all odd squares of odd numbers can be written as sum of consecutive natural numbers. Now let's take the example of 121. So if we say that 121 can be written as 60 plus 61, that doesn't mean that 121 cannot be written as sum of any other two numbers. 121 can also be written as 120 plus 1. It can also be written as 100 plus 21. But one of those possible expressions could also be 60 plus 61. So basically, this relation holds true only for square of odd numbers. Do you want to try with a square of even number? Okay, let's take the example of 36. So 36 is the square of 6, which is an even number. So in this case, do you think that 36 can be written as sum of two consecutive natural numbers? So see, one option you can write 36 is 18 plus 18. Another option you can write it is 16 plus 20. One more option could be 17 plus 19. So these are the various options. In fact, there are many more options in which you can write 36. But you will never come across an expression where 36 can be written as sum of two consecutive natural numbers. So when you look at 16 and 18, 16 and 20, they are not consecutive. 17, 19, again, they are not consecutive. 18, 18, they are equal and not consecutive. So therefore, the squares of even natural numbers, this rule doesn't hold true. Now, whenever you are given square of an odd number, how will you write it as sum of two consecutive natural numbers? For example, 169 is one more example, which is a square of an odd number. 13 square is 169. So how can you write this as sum of two consecutive natural numbers? Because for smaller numbers, it was comparatively easy to find out those two consecutive natural numbers whose sum is equal to that number. But as the number becomes bigger, how do you handle this? So to find this out, that it is the sum of which two numbers, what you do is the given number minus 1 divided by 2 would be one number, and the given number plus 1 divided by 2 would be the other number. So given number is 169 minus 1 divided by 2. This would be one number, and given number plus 1 divided by 2, this would be the other number. So basically, these two numbers are like, to first find out the midpoint of the given number. Like you're talking about 169. So if you divide 169 into two equal halves, that is, you divide 169 by 2. So how much do you get? So 169 divided by 2 is 84.5. So that means two numbers which lies exactly before and after, that is two natural numbers close to 84.5, they would add to give 169. So one number could be 84, the other number could be 85. So with this calculation also you would get the same thing. This would be 168 by 2. So 2 8s is 16, 2 4s are 8, and this would be 170 by 2, which is 85. So 169 can be written as the sum of 84 and 85. So this is how you find out which two numbers sum would be equal to 169. So the given number minus 1 divided by 2 and the given number plus 1 divided by 2. So the concept is somewhat like this. Let's say this is your 169. So if you want to write 169 as sum of two things, so what we are trying to do is we are dividing 169 into two equal parts. Now the sum of these two equal parts will be equal to 169. right? Now, when you exactly divide it into two equal halves, so each half is 84.5. But we are looking for natural numbers. Therefore, what we do, for one number, we subtract 0.5. We get 84. For the other number, we add 0.5. So, we get 85. So, 84 plus 85 also gives us 169. So, this is the logic behind this interesting pattern number 2. Now, let's move on. So, this was indeed interesting, right? Because we never thought that numbers in themselves can be so interesting and creative, but yes, they are. And that is how we have this entire branch of mathematics which deals all with numbers. Now let's move on to another interesting pattern 3. So let's see, what do we have here? So you would have seen that perfect squares of numbers formed by same digits form beautiful patterns. Now, these patterns which we are going to talk about now, these patterns are not formed for all numbers. These are formed only for some specific numbers where the same digit gets repeated over and again. So let us look at some examples. For example, 4 square is equal to 4 into 4, which is 16. 34 square. So if you actually find out the square of 34, it is 1156. Now look at the square of this number, 334 square. So the result is 111556. Now if you even increase one more 3 in the number, instead of 334 you now have 3334. So its square becomes 11115556. So just look at the pattern. So do you think that it is again making a very interesting pattern? Yes, it is. Now this is, I really do not want to tell you that it happens with all the numbers. It happens only with some specific numbers, and especially with those numbers where you have repetition of digits. Like here you see the digit 3 is getting repeated over and again. So if you compare the numbers for whose squares you see this pattern, you see that initially there was no 3, then 1 3, 2 3, 3 3s, 4 3s, and so on. So it happens only with these kind of numbers where you repeat digits. Let's look at one more pattern here. It's 11 square is 121, then 101 square is 10201, 1001 square is 100201. So you see what happens is, as the number of zeros between the two ones is increasing on the left hand side, the number of zeros on the right hand side are also increasing, and these are like the real values. So it's very amazing to see that these are real calculations, and with numbers you have such beautiful things existing. Now looking at this, if I ask you that what would be the square of this number, so I increase one more 0. So very easily, looking at the pattern, you do not need to do the multiplication at all. Just by looking at the pattern, you can say that earlier there were 5 zeros, now this would be 6. So this becomes like this. So this side, instead of 4 you have 5 zeros, this side also instead of 4 you should have 5 zeros. So just by looking at the pattern, you can tell squares of even bigger numbers than these. Like in this case also, if I tell you what would be the square of this number, so I have increased one more 3. So what would happen? So the number of ones earlier was 5, so I increased the number of 1. Again, earlier there were 4 5s, so I increase 5 also by one more, and 6. So just by looking at the pattern without doing actual multiplication, you can actually predict squares of some bigger numbers as well. So let's try this one. Observe the following pattern and supply the missing numbers. So here again you see a similar pattern, and you have to fill up the blanks. So see here what's happening. First, for these kind of questions, first you have to very carefully observe the pattern that is taking place. What is the pattern that is being followed? For example, here what happens is, as you increase a 0, in between the number of zeros increased here, in between 1 and 2s. Here again you increased one more 1. So basically earlier you just put 1 0. Now you have put 0 1 0. Now you have put 0 1 0 1 0. So gradually as you are increasing the number, so what is happening to the pattern? So earlier it was 1 to 1, there were no zeros in between. Then it became 1 0 2 0 1. Then it became 1 0 2 0 3 0 2 0 1. So basically what's happening is at every step we see that a new number is getting introduced. Like earlier it was 1 to 1, then 20 was introduced in between. Then in the third step 30 was introduced in between. So what will happen in the fourth step? What do you think? So in the fourth step, 40 will get introduced in between. So you will have 40 in between. And then on the left hand side, you would have 10, 20, 30. And on the right hand side, what will you have? 30, 21. So this would be your next number, because just look at the pattern. Earlier it was 1 to 1. Then it was 10, 20, 1. Then it was 10, 20, 30, 21. So next it is 10, 20, 30, 40, 30, 21. Because here we are observing that if you look at, especially at this step, it becomes clear that you have 30 here, 10, 20 on this side also you have 20, but the last digit is always 1. So now that you have increased the center number to 40, so this side you will have 10, 20, 30, this side you will have 30, 20. So in the fifth step, you see the center number is 50. So now you have 10, 20, 30, 40. This side you have 40, 30, 20. But this time, what would be the number this side? Now let's see how the pattern is increasing on this side. Earlier it was 11. Then it was 1, 0, 1. So what was the change? 1 0 was inserted in between the two ones. Next was 1, 0, 1, 0, 1. So what is happening? You see an extra 1 0. So from this step onwards, you see at every step this 1 0 is an extra thing that is getting added. So initially it was 1 0 1. So here one extra 1 0 got added. So it became 1 0 1 0 1. In this step, one more extra 1 0 got added. So it became 1 0 1 0 1 0 1. So what will happen in this step? One more 1 0 will get added, and then this entire number, that is 1 0 1 0 1 0 1. So in this fashion, just looking at the pattern and analyzing it well, you can fill up the blanks given in the pattern. So now based on whatever we have learned about perfect square, like mostly the properties of perfect squares, how do we distinguish which is a perfect square and which is not, let us have a quick summary. So this summary will actually help you to distinguish or identify which number is a perfect square and which number is not. So first thing is, if the number ends in 0, 1, 4, 5, 6 or 9, then it must be a perfect square. So this is one very easy way of determining whether a number is a perfect square or not. So first look at these digits. Next is, perfect squares can only have even number of zeros at the end. So if you have numbers ending with zeros, for example, if you had something like 3000, so is this a perfect square? No, because the number has 3 zeros, odd number of zeros, so it is not a perfect square. But if you have something like 2500, so is this a perfect square? Yes, because it has even number of zeros, so this is a perfect square. If a number is a perfect square, it has to be the sum of successive odd numbers starting from 1. So any number, any damn number which is a perfect square, it has to be the sum of first n odd numbers. That is why we say that the sum of first n odd numbers is n square. So that n square is a perfect square. So for example, if we take the same number 2500. Now you might ask that 2500 is such a big number. So how do we know that if it is actually, sum of first n odd numbers or not? So this 2500 is your n square. So if you find the value of n, so in this case 2500 is the square of 50. So that actually means that 2500 is the sum of first 50 odd numbers. So in this fashion, like here you have written 1, 2, 3, 4, 5, 6. So in this way you have to write 50 first odd numbers. So 2500 is the sum of 50 first odd numbers. In fact, any number which is a perfect square, it must be expressed as sum of successive odd numbers starting from 1. If a number is a square of odd number, then it should be expressed as a sum of consecutive natural numbers. Like as I said, that square of odd numbers, like 9 is a square of odd number because 9 is 3 square. So 9 should be written as sum of two consecutive natural numbers, like sum of 4 and 5. Similarly, if you talk about, let's say, 121 is the square of odd number 11. So if this is written as 60 plus 61. So which are again consecutive natural numbers. So basically these are some of the basic properties of perfect squares, looking at which you can very easily identify whether a given number is a perfect square or not. Now, when we are talking so much about squares, you might be thinking that, okay, for smaller numbers it is fine. But for larger numbers, finding their squares by actual multiplication could be difficult. So how do we find squares of larger numbers? So let's take an example. Let's say that I ask you to find out the square of 64. So 64 square is not something which you can quickly say or which you can calculate mentally and just give the answer. So that's not possible. So what would you normally do if I ask you to find out the value of 64 square? So you will perform actual multiplication. That is, you would multiply 64 by itself. So 4 into 4 is 16. 1 gets carry forward. 6 into 24 is 24. Plus 1, that is 256. Now 6 4s are 24. Again 2 is carry forward. 6 6 36. Plus 2, that is 38. So now you add both of these, it becomes 6, 9, 10, 4. So the result is 4096. Now you can do this actual multiplication and find out the square of 64. But the chances of mistakes or chances of error in this actual multiplication is more, because you are doing a lot of calculation. You're doing multiplication, you are doing addition. Now when your numbers go even bigger, like 64 is one example. Now if I ask you to find out the square of 642 square, so the multiplication is going to be more tedious. So the chances of error is more. So to avoid that, we often follow this particular method where we do not do actual multiplication, but we do something by which the method of calculation becomes little easier. So 64, we can write 64 as 60 plus 4. Now why did we write it like this? Because whenever we have something like 40, 50, 60, so whenever we deal with numbers ending in zeros, calculation by default becomes easier. So that is why we want to represent the given number in terms of a multiple of tens, like 60 is a multiple of 10. So 64 we want to write as 60 plus 4. So 60 plus 4 square. So what does this mean? This means that 60 plus 4 is getting multiplied to itself. That is 60 plus 4. Right? Now how can we write this? Now let's say that if you would have had something like this, x plus y into z. How can you write this? So if you have x plus y inside the bracket multiplied by z. So this is same as x into z plus y into z. This is the same thing, that x multiplied to z plus y multiplied to z. So this would be the same thing. So in a similar way, we are going to do the same thing here, where 60 is your x, 4 is your y, and 60 plus 4 is your z. So therefore, we can write it as 60 into 60 plus 4 plus 4 into 60 plus 4. So now this becomes 60 into 60. So this is the distributive property, if you remember. So this is how distributive property works. A into B plus C can be written as A into B plus A into C. So 60 into 60 plus 60 into 4 plus 4 into 60 plus 4 into 4. So now this multiplication is less tedious because you have zeros. So 2 zeros multiplied, you would get double 0. 6 into 6 is 36. 6 4s are 24, 1 0. Again 6 4s are 24, 1 0. 4 into 4 is 16. So when you sum these up, you get 4096. So you get the same answer. The only difference, and in both the cases you take some amount of time. But the only advantage is that in this case, using this technique of taking the help of distributive property, the chances of making calculation mistakes is lesser, because this time the calculations that you are performing are simpler than what you were performing before during actual multiplication. Let's take one more example. Okay, so I think I have overwritten that. So let's say this is our next example. 102 square, 102 square. So how can we write 102? This can be written as 100 plus 2 whole square. So this would mean 100 plus 2 into 100 plus 2. So with the similar approach, we can write 100 into 100 plus 2 plus 2 into 100 plus 2 using the same property as we discussed here. So this becomes 100 plus 100, 100 into 100 plus 100 into 2 plus 2 into 100 plus 2 into 2, that is 4. So this becomes 10,000, this becomes 200, this becomes 200, and this is 4. So when you find out the sum, it is 10404. So you see here also there was no need to perform actual multiplication, and you could very easily find out the square of 102. Let's try to find out squares for numbers ending with 5. That is, those numbers which have 5 at their units place or the ones place, whatever you call it. So this is the units place or ones place, this is the tens place. So let's say that we have a number 45 and you have to find the square of 45. So here also we will not do actual multiplication. Instead, we will follow the same technique. But here we will see one interesting thing. Now that you have 45, how can you write 45? You can write it as 40 plus 5 square. So this can be written as 40 plus 5 multiplied to itself, that is 40 plus 5. Now again with the same logic, this can be written as 40 multiplied to 40 plus 5 plus 5 multiplied to 40 plus 5. So this becomes 40 into 40 plus 40 into 5 plus 5 into 40 plus 5 into 5. So 40 into 40 is 1600 plus 200 plus 200 plus 25. So this comes out to be 2025. So this is the square of 45. Now one interesting thing that you observe is whenever you are trying to find out square of a number which ends with 5, the square also ends with 5. So you see 5 square is 25. So it's quite obvious that square of any number ending with 5 will always have a 5 at the end. In fact, there is one more similarity. Let's look at one more example. So that would help you to understand it better. So let's say that we take 155. So 155 would be 150 plus 5 whole square. So that would be 150 plus 5 multiplied with 150 plus 5. Okay, I think it was 175. Okay, now let's consider it 155 because we already started off with the calculation. So this can be very well written as 150 multiplied to 150 plus 5 plus 5 multiplied to 150 plus 5. So this becomes 150 into 150 plus 150 into 5 plus 5 into 150 plus 5 into 5. So when you find out the product, you see it's 22500 plus 750 plus 750 plus 25. So you see here also at the end the fourth term was 25. Here also the fourth term is 25. And this happens for all numbers which ends with 5. So in whichever number you have the units place is 5, you normally get to see this trend where out of these 4 terms, the last term would be 25. Now a lot of people, they give some specific formula with regards to these numbers ending in 5s. But I really do not believe in, memorizing formula and then putting things into formula. So you follow the same approach as you do for all other numbers. But this is some something different that you observe. Not different, I would say this is something unique about these numbers ending in 5. So that's why I brought it to your notice. So this time your result is 24025. Again, a number ending in 5. So this is one very simple way which we discussed, by which you can find out squares of numbers without doing the actual multiplication. So it's question time now. Let's look at some questions. Question number 1. What will be the unit digit of the squares of the following numbers? So let's see what are the numbers given to us. Okay, we have 3 numbers here. So let's look at the first number, 1, 2, 3, 4. So whenever you have to decide the unit digit of the square of that number, we just focus on the unit digit of that number. So here the unit digit is 4. And we know that 4 square is equal to 16. So that means when you find out the square of this number 1, 2, 3, 4, it is very obvious that the unit digit of the result would be 6. No matter what the other digits are, but the unit digit will definitely be 6. I think we have discussed in detail that even if you perform actual multiplication, you would see it very clearly that finding out square means you are multiplying 1, 2, 3, 4 with 1, 2, 3, 4. So obviously the last digit is decided by the multiplication of the unit digits of the number, that is 4 into 4, which is 16. So the last digit, that is the units digit, would be a 6. For the second number, 5, 2, 6, 9, 8, which is the unit digit? It is 8. So when you find it square, you know that 8 square is 64. So can you tell me what would be the unit digit when you find it square? So the units digit would be 4. Let's look at this one, 5, 5, 5, 5, 5. So last digit, units digit is 5. So obviously the unit digit of the square would be 5. That's because 5 square is 25. Question number 2. The following numbers are obviously not perfect squares. Okay, we know that they are not perfect square. We just need to give the reason that why they are not perfect squares. Okay, 2, 3, 4, 5, 3. Now we have discussed about a few rules which help us to decide whether a number is a perfect square or not. So let's quickly recall those rules. So by looking at a number, how can you say if it is a perfect square or not? The very first thing that you try to observe is which is that digit in which the number ends. That is basically you try to look at the unit digit of that number. So here if you focus on the unit digit, it is 3. Now any number which ends in 0, 1, 4, 5, 6 or 9, they are perfect squares. But 3 is not one of them. So since this number ends in 3, this tells us clearly that this is not a perfect square. Why? Because when you look at the first 10 perfect squares, you see that all these digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all of these digits square, they end either in 1 or 4 or 9 or 6 or 5. So if you have anything other than these, definitely that number is not going to be a perfect square, because whichever number square it is going to be, they would be one of these digits, right? So if you multiply 2 same digits, you have to get either 1, 4, 9 or 6 or 5 at the end. That's it. So you cannot get a 3 at the end. So therefore this is not a perfect square because it ends in 3. Next one, here you have a number which ends in zeros. So it ends in 0, so obviously it can be a perfect square. But how many zeros it has? It has 3 zeros. That is, it has odd number of zeros. And a number ending with odd number of zeros is not a perfect square. Third one, 8, 9, 7, 2, 2. Again, you focus on the last digit, it's a 2. So do you have a 2 here? No. So therefore, since it ends in 2, so it cannot be a perfect square. Question number 3. The squares of which of the following would be odd numbers? So we are given 2 numbers and we have to tell if we square these numbers whether their squares would be odd or not. Now we have observed and proved and learned that square of an odd number is always odd, square of even number is always even. So looking at these numbers, 4, 3, 1, is it odd or even? This is odd. So therefore its square would also be odd. Similarly, when you look at this 7, 7, 7, 9, is this even or odd? This is again odd. So its square will again be odd. So how do we distinguish between even and odd numbers? I hope you know that. If you have forgotten it, just for a quick recap, any number which ends in 0, 2, 4, 6 or 8 is an even number. All others are odd numbers. So here you see it doesn't end in any of these. So the number should end in one of these digits. So only then it would be an even number. So this is the criteria for a number to be even. Question number 4. Using the given pattern, find the missing numbers. So if you look at this pattern, you have some gaps at certain places. Like you have a gap here, you have a gap here, you have a gap here, and also a gap here. So you need to fill these gaps. So here, if we observe it carefully, we would see some pattern. So let's observe the pattern. So what do we see here? 1 square plus 2 square plus 2 square is 3 square. Then 2 square plus 3 square plus 6 square is 7 square, and so on. So looking at this pattern, what are the observations that we make? So we make few observations. The first observation is that the second term is 1 more than the first term, like the number in the second term. So here if the number is 2, here it is 1. If the number is 3, here it is 2. So basically the second term is just 1 more than the first term. So if the first term is 2, second term is 1 more than the first term, that is 3. If the first term is 3, the second term is 4. So this is one thing that we observe. The second observation is that fourth term is 1 more than the third term. This is our fourth term. Okay, let's call this as the first term, second term, third term, and fourth term. So just so that the explanation becomes easier. So you see the fourth term's number is also 1 more than the third term. Here it is 2. So that if the third term is 2, the fourth term is 3. 1 more than 2. Similarly, if the third term is 6, fourth term is 7. If the third term is 12, fourth term is 13. So this is our second observation. So with this second observation, we can quickly fill this gap. So if this is 21, this will be 1 less than 21. So this should be 20. So we have already filled one. Perfect. Okay. Let's move on to our third observation. Okay. With our first observation that the second term is 1 more than the first term, we could have filled this. So if this is 3, this is 4, this is 4, this is 5, this is 5, this is 6. Right? Okay. Now what is our third observation? So our third observation is that the third term is, look at the third term. So the third term is n times the first term. Like you look at the first row. Here if this is 1, what is the third term? Third term is twice of the first term. Let's look at the second row. Here, the third term is 3 times the first term. So like for the first case, if you see, this term is 2 times the first term. In the second row, this term is 3 times the first term. In the third row, this term is 4th time the first term. So basically, with each row, you see, this is increasing. Like in the first row, 1 multiplied by 2 gives you 2, which is the third term. In the second row, 2 multiplied by 3 gives you 6, which is the third term. In the third row, 3 multiplied by 4 gives you 12, which is the third term. So in this case, 4 multiplied by 5, because this value is also increasing with each row. So 4 multiplied by 5 is 20. So that's how also you see whatever we wrote 20, that is correct. So here it should be multiplied by 6. So 6 into 5, 30. So you see third term is 30. So now with this we will be able to fill our last blanks. So this time you will multiply by 7. So 7 into 6 would be 42. So this term would be 42. So now if this term is 42, what would be this term? So as per our second assumption that the fourth term is 1 more than the third term. So this would be 43. So here overall we made 3 different observations. So first observation was second term is 1 more than first term. Second observation was third term is 1 more than the second term. Fourth term is 1 more than the third term. And the third observation was the third term is n times the first term, where n's value is increasing from 2 gradually at each row. So when we say first term, second term, we are not talking about the overall value of the first, second or third term. We are just talking about the base of the first, second and third term respectively. Question number 5. Without adding, find the sum. Okay, so what are the set of numbers that is given here? We see that these are set of some odd terms, odd numbers. Now when you observe more closely, you see that these are the odd numbers, the consecutive odd numbers starting from 1. So how many odd numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So therefore the number of odd numbers that we have is 10. So the sum of n odd numbers is always given by n square. So n square would be 10 square, that is 10 into 10, which is 100. So the sum would be 100. So even though we didn't perform actual addition, but we could find the sum of these numbers. Question number 6. Express 121 as the sum of 11 odd numbers. So when you look at 121, so 121 is nothing but 11 square. So 11 here is n. So n square, that means the sum of first 11 odd numbers. So which would be the first 11 odd numbers? So let's start from 1. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21. So these are the first 11 odd numbers. So 121 can be expressed as a sum of the first 11 odd numbers. Question number 7. How many numbers lie between squares of 25 and 26? So square of 25 and square of 26. Now it is extremely tedious to find out the actual value of 25 square and 26 square, and we really do not need to do that also. What we have learnt is between the squares of two consecutive numbers there exists many non-perfect squares. So there will exist many such numbers which are not perfect squares between 25 square and 26 squares, and there are some specific number of such numbers existing between two consecutive squares. So how many numbers exist? So we have learned that between squares of two numbers n and n plus 1, how many non-perfect squares will exist? 2n number of non-perfect squares will exist. So 2n number of, so what is the value of n here? So n here is 25. So in this case n is 25 and n plus 1 is 26. So that means between squares of 25 and 26, how many perfect squares will exist? 2n number of perfect squares, that is 2 into 25, which is 50. So 50 numbers lie between the squares of 25 and 26.
I hope you found the video useful, and if you really understood the concept well, do write in the comment section that concept hua crystal clear. And I will see you all very soon with a new topic and a new video. Till then, take care. Bye-bye.